Hello students, in today's video, let us learn about vibrations of crystals. Specifically in this video, we will be looking into the vibration of crystals with monoatomic basis, meaning there is only one kind of atom present in the whole basis. So we know when elastic waves propagate through a crystal, the atoms in the crystal will be moving in phase with the vibrations or with the waves. So the frequency of the propagating wave will oscillate different atoms along its mean position. So when we consider different waves propagating through these crystals, the simplest kinds of waves are those which propagate along the directions 100, 110 or 111. When we say 100, the wave will be propagating along the x direction. So in 111, the wave will be propagating diagonally. So in those cases, it is easier to assume different planes and to assume different motions that are achieved by different planes. Now when a wave propagates through such crystals, as indicated in this figure, different planes will be oscillating along its mean position. So here this dashed lines represent the mean position of all the planes, and this solid curves, solid lines represent the position of different planes when the wave is propagating. The wave vector of the wave is k. So as you can see, one plane will be in its mean position. The next plane will be displayed slightly, whose position will be us plus 1. The next plane will be displaced by us plus 2 and so on. So after a while, this displacements will change, so creating a kind of oscillation along the mean position, and that is how this wave will propagate through this crystal lattice. Now when we consider the motion of atoms, these displacements can be in two different types. One is the displacement of these planes or these atoms can be along the direction of propagation of the wave as indicated in this figure, or these atoms can move perpendicular to the direction of propagation of wave. So we call them longitudinal waves and transverse waves, right? So this is the representation of a longitudinal wave. Here, as you can see, the wave vector represents the direction of propagation of wave, and it is along this direction. Here, different atoms are also moving along that direction itself. So this is a longitudinal wave. In a similar manner, the atoms can be displaced along the direction perpendicular to the motion of the wave. So here you can see a transverse wave. The wave vector is along this direction, the positive x direction, but the atoms are being displaced perpendicular to the direction of motion of wave. Similarly, there can be two different transverse waves. These atoms can also be displaced in a perpendicular direction into the plane of this page. So that will constitute the other transverse polarization. So there are two transverse polarization. There can be two different perpendicular directions perpendicular to the propagation vector k, and there is one longitudinal polarization which is along the direction of propagation of wave. Now let us think about the solution of the wave propagation through a crystal lattice. We will be looking into obtaining the dispersion relation, which is the relation between the frequency of the wave and the wave vector k, and also the relation between the lattice vector A and so on. So we will be looking into obtaining this dispersion relation. For that, we will have to assume certain fundamental observations. So we assume that the force on the plane S caused by the displacement is actually proportional to the displacement itself. So you are thorough with the Hooke's law that you have learned in your lower classes. What is Hooke's law? It is F is equal to minus kx. or force is proportional to the displacement, right? So in a similar manner, here we assume that the force is proportional to the difference in the displacement. So we can write F will be F on the plane S is actually proportional to US plus 1 minus US, which is the relative displacement between two adjacent planes. Similarly, for the S plane, there are two adjacent planes. One is US plus 1, the other one is US minus 1. So let us add that term to. The force S will also be proportional to US minus 1 minus US. So effectively, I can write an equation based on our concept about Hooke's law. So the force acting on the S plane due to its displacement from the mean position will be equal to a constant into US plus 1 minus US plus constant into US minus 1 minus US. This constant is the force constant between two neighbor planes. Now let us write the equation of motion of the plane S. For that, we know we can represent force by m into d square displacement by dt square, right? M into acceleration, mass into acceleration is force. So let us replace this term of Fs by m into d square us by dt square, which will be our equation of motion. So it is m into d square us by dt square, which is equal to c into us plus 1 minus plus us minus 1 minus 2 us. So this is the equation of motion of the S plane. Now we look for solutions where the displacements have a time dependence given by exponential minus I omega t. So if this is the time dependence of the displacement us, what will be d square us by dt square? So you have to differentiate this term twice with respect to time. So we know we will get omega square twice, minus I omega twice, minus I omega into the us term. So if you differentiate us with respect to time twice, it will add a constant minus omega square alongside us. So if in this term m into d square us by dt square, we can write it will be simply minus m into omega square into us, because d square us by dt square will be simply minus omega square into us. So this is equal to c into us plus 1 plus us minus 1 minus 2 us. This is a difference equation in displacement u, and the solution of this kind of equation is a traveling wave, and which is given by us plus or minus 1 is equal to u into exponential iska into exponential plus or minus ika. So this equation means that us plus 1 will be u into exponential iska into exponential plus ika, that is us plus 1 is u into exponential I into s plus 1 into ka. Similarly, us minus 1 will be u into exponential I into s minus 1 into ka. Now substitute for this us plus 1 and the similar equation for us minus 1 into our equation number 1. So substitute for us as exponential iska, us plus 1 and us minus 1 by their respective equations. You can obtain minus omega square m into u into exponential iska is equal to c into u into exponential I into s plus 1 ka plus exponential I into s minus 1 into ka. This is us plus 1, us minus 1 minus 2 us. 2 into exponential iska. Now you can cancel out exponential iska in all the terms. So the resulting equation will be omega square m is equal to minus c into exponential ika plus exponential minus ika minus 2. Now we have the identity 2 cos ka is equal to exponential ika plus exponential minus ika. So substituting for these terms as 2ka, we can obtain omega square is equal to 2c by m into 1 minus cos ka. Cancelling out this negative sign by taking it inside the brackets and substituting for 2 cos ka as exponential ika plus exponential minus ika, we can obtain the relation between omega square and ka as in this equation. Here k is the wave vector, a is the lattice constant, that is the distance between two adjacent planes. Omega is the frequency of the wave that is being propagated through this crystal. Now we know the boundary of the first Brillouin zone is given by k equal to plus or minus pi by a, right? Now let us calculate the slope of omega versus k curve at the zone boundary. So we have the relation between omega square and k. What will be the slope of this equation? It is given by the derivative of the function d omega square by dk, which will be 2ca by m into sin k. Now we know at the zone boundary when k equal to plus or minus pi by a, d omega square by dk will be equal to 2ca by m into 2 sin pi by a into a, which is sin pi, which is 0. So its value will be 0. So we know at the zone boundary the slope of the curve omega square versus k curve will be 0. Now let us use one more trigonometric identity in order to simplify this dispersion relation between omega square and k. So we know 1 minus cos ka is sin ka by 2 into 1 by 2, right? So it is given by 1 minus cos ka is equal to 2 times, not 1 by 2, 2 times sin square ka by 2. So let us substitute for 1 minus cos ka. Now omega square is equal to 2c by m into 2 times sin square ka by 2, which is equal to 4c by m into sin square ka by 2. So what will be omega? Omega can be written as root of 4c by m into modulus of sin ka by 2. Now if we plot omega versus the wave vector k, let us look at the graphical representation of this relation. So if you plot k along the x-axis and omega or omega by root of 4c by m along the y-axis, the curve will look like the mod sin ka by 2 curve as indicated in this figure. So minus pi by a and plus pi by a are the zone boundaries, and as you can see here, the slope of this curve is 0 at the zone boundaries. And you can see that within the first Brillouin zone, we have different values for omega, and in the next Brillouin zone, we will actually have a repetition of the same curve. So this will have an implication on defining the first Brillouin zone, as we will see later. So this is the relation between omega, the frequency of the wave that is propagating, and the wave vector k. I hope this portion is clear for you. We have simply looked at the mode of propagation of different waves. We have tried to write down the equation of motion of different planes, and from that we obtained the dispersion curve and we plotted the graphical representation of this dispersion relationship. I hope this portion is clear for you. Thank you.